computing capture tubes with interval analysis. So it is a common work with other colleagues from Bretagne, Jordan Ninin, Mohamed Saad, also some other people from Nantes, like Gilles Chabert, University of Manchester, Alexandru Stancu, and colleagues from MBDA, such as Stéphane Menec and a student, Vincent Doze, who is a student internship in MBDA, but also comes from Bretagne. So before introducing the notion of capture tube, I will recall what means the V stability. So V stability has been used in the context of VEMOS. So VEMOS is a sailboat robot. Here, he has at the top of the wind sensor. Inside the hull, you have compass, inertial support, GPS, and you have a balance wing system. And it is totally autonomous. It's able to go to 1.1 here in the lake of Angers for a special day on robotics. So it has to go during 2 days inside the lake. This boat has gone west to Gudenberg. It has been made in Bretagne, especially by Patrick Rousseau and Olivier Menec from and all algorithms have been implemented. So now, what you have in VEMOS, you have first the sailboat. You can control on the sailboat the rudder, delta R, and also the maximum length, the maximum angle of the sail, thanks to a main sheet. So you can control the length of the main sheet. You have some sensors, such as the GPS, that give you the position M of the boat. You have the heading theta of the boat, and you have C, which corresponds to what is measured by the wind sensor at the top of the mast, which corresponds to the direction of the wind. From M, theta, and C, you have a controller. You give in this controller A and B, which corresponds to the line you want to follow, and the controller will compute automatically the angle for the rudder and for the sail, so that the robot will be able to accomplish, to follow the line AB. That is the idea of the controller. Here it is an experiment where you have the square spiral experiment, where the boat starts from here. So first it starts with a small triangle, as usual, to see that everything is okay. Then it has to follow this line, so you can see it in red. And what has been done in green, what is painted green, is the actual trajectory that VEMOS has actually done. So it has performed the square spiral, as explained here. Then it has waited for maybe 30 minutes around the point. It is a station keeping problem. And then it came back to the harbor. So they're here and here. Okay, it is a typical mission of VEMOS, something like 20 kilometers, something like this. So we can see here that VEMOS is able to stay inside a corridor around the line it has to follow, the red line. So now, VEMOS with the controller can be described to be simple as a state equation, x dot equal to f of x. So for VEMOS, you have the state space can be decomposed into two parts. The part where you are x1, where you are outside the corridor you have to be, and inside the corridor, it is x2. So what we want to do is for differential equation, state equation like this one, we want to prove that if you have in x1, we will leave one day x1 to enter inside x2. And once we'll be in x2, we will stay inside x2 forever. That's what we want to prove for differential equation. This is important to, so we will say that x2 is a capture set. It's important because after we'll define capture tubes, we can be seen as something like a capture set which depends on time. So how can we prove that x2 is a captured set? So we introduce the V stability. So the V stability, for the V stability, you need to have some kind of function V. And when this function V depends on the state X, from Rn to R, it is not very positive. So V looks like a Lyapunov function, but it is not exactly a Lyapunov function. When this function V is positive, then it will decrease. So in this case, we'll say that the system is V stable. Of course, V dot, the derivative of V with respect to time, can be expressed as follows. So we have an expression for V dot of X. So if you want to prove that a system is V stable, can be solved using interval analysis. So how can I prove this implication using interval analysis? First, I have to notice that A imply B is equivalent to say. So A and B here are proposition. This is equivalent to say that either B or, this means or, A is false. So A implies B is equivalent to say that either B is true or B or A is false. Okay. So now, due to this, I know that this is equivalent to say that V dot of X negative, so this corresponds to that, or V of X is negative. Okay, so this is the negation of that. So if you prefer, this corresponds to A, this corresponds to B, this corresponds to B, and this corresponds to not A. Okay, so now, if I have this, I should have inserted before for all X. Because when I write such an implication, it means implicitly that it is the case for all X. But here I have to add for all X. Now, for all X, this is true if the negation of this proposition is inconsistent. So I will take the negation of this proposition. So let's call this composition C. I will say that C is true if non-C is inconsistent. So the negation of this proposition corresponds to there exists X such that, so I have to recall the De Morgan rule, which say that the negation of A or B is equal to the negation of A and the negation of B. So this is the De Morgan rule. So I will use it now. The contrary of this is V dot up, sorry, here maybe I have forgotten something. Oh yes, here it's V dot. Okay, so here I will write V dot of X positive and, so V of X is positive, like this. So inconsistent. So let me recall that this is true if I have all this. So it means if that the negation of this is inconsistent. Okay. So in fact, I have to prove that the system of this system of inequalities is inconsistent. Now, since I know that x dot is equal to f of x, so it is a case for when I have a dynamic system, then due to this, it implies that v dot of x is equal to derivative with respect to x multiplied by x dot, which is equal to the derivative of v with respect to x multiplied by f of x. So if you want, I know that I have an analytical expression for v dot. Thus, I have to prove that the system of nonlinear inequalities has no solution, and this can easily and efficiently be performed using interval analysis. So if you want, what means this? It means that I have, I will draw a small picture. I have here a set where v is negative. V of x is negative, and outside this set, v of x is positive. Okay. Now, when I am, if this is inconsistent, it means that I cannot find one point such that v is positive, like this one, and where the derivative v dot is positive. So I will try to show how it works. So here I draw an arrow which represents here x, here f of x, which corresponds to x dot, and here in green I will represent a level curve of V. So for instance, here I have V of x, which is equal to 5, let's say 5. Here, just here, V of x is 0. Here it is 5. If I have this situation, it means that V dot is positive because, so V dot is clearly positive, so I'm going out. So if I have this situation, then I am not V stable. So of course we understand that if this is not the case, all arrows will be like this. Okay, and in this situation, it is clear that all trajectory starting from one point x will decrease with respect to v, and one day they will enter in the set v of which corresponds to an equality v of x negative. Once they are here, the trajectory can do anything. They could, for instance, follow a limit cycle or anything else. Okay? So in fact, this theorem here, let's say that I can transform the V-stability problem into a set of inequalities. Here I have a picture that I've explained just on the picture before, and I am able to prove with this tool that a set described by inequalities is a capture set. Now I will try to extend the notion of capture set to capture tube. So a tube, what is a tube? It is a function, it is a set which depends of time. So if you want, it associates to any time a subset of the state space Rn. So if you want, it may correspond to a bubble that moves with time. So if you prefer, maybe to draw this to make it more clear, if here I have my, let's say, my state space like this. So here it may correspond, for instance, to x1, here x2. If here at time t1, my set is like this. At time t2, it is like this, and this can decrease with time, and then it can increase with time, like this, whatever. It can be seen as a bubble which moves with time. So it's a graphical interpretation of what is a tube. It is not necessarily a capture tube. A capture tube will be a specific tube where when you have a dynamic system, once the state is inside the bubble, it will stay inside the bubble forever. Okay, how can I represent inside the machine a tube? So I can represent inside the machine as a discretization. Here, for instance, I will have the time t, and here I will have, for instance, the state space can correspond, for instance, to x. Okay. So I will have many slices with a corresponding sampling of the time, discretization of the time. So it is a possibility to represent a tube inside the machine. There is other possibilities, mainly presented by Moore. You can represent a tube by a function which depends of time t, but which involves some intervals to represent the uncertainty of some parameters, for instance. So you will have here f of t may correspond to interval function which depends on t, but also you can have interval polynomials such as j, and in this case you can also provide some integrals to add these tubes and some kind of arithmetic on tubes if you use this formalization. In our context, we'll mainly use this representation for the tubes, so with a discretization of time. Okay, now what is a tube? A capture tube. A capture tubes, first I need a capture tubes, first I need a dynamic system. So dynamic system is x dot equal to f of x and t, where x is a space, and the tube is a set which depends on time. So if I come back here, if you want, there you have j of t1. Here it is j of t2. And another possibility to represent this, maybe more comfortable for us, will be the following. You have here, here, and here the time t. Here you will have the state x. And there, for instance, here you will have a tube which can be represented like this for t max. Oops. Okay, this is a tube. So this can be corresponds, for instance, to j of t. Here, for instance, you may have t1, and this interval here may correspond to j of t1. So it is a tube. What is a capture tube? A capture tube, you have a dynamic system, as explained just before. You have a dynamic system which tells you that x dot corresponds to f of x and t. So if I am at time t, I am here, I will have some kind of direction thanks to f, which tells me how x will move. We can understand at this moment that a capture tube is a tube such that if I have a trajectory like this, I can move like this. Once I am inside, I will stay inside forever. It is a capture tube. Another capture tube is this one, of course. It is another capture tube. I have maybe one which is not a capture tube. For instance, black. Enter inside. Up to now, everything is good. But here, it is this trajectory may be a counter example that tells me that j of t is not a capture tube because I was inside and I was able to go out. So if I have such a trajectory with this, I can say that it is not a capture tube. As we'll see later, what happened to prove that I have a capture tube, I will have to prove that such a situation like this will never appear. Okay. So I will try to find such a point where trajectory could go from inside to outside. And if I can prove that it is not possible, then I will have a proof that J is not a capture tube. Okay, so let me come back. I have a dynamic system and a tube. A tube is said more formally, it's said to be a capture tube if I am inside, X is inside the tube, and if I take any tau positive, then the trajectory at time t plus tau belongs to the set at time t plus tau. The following theorem will make it possible to prove that we have a capture tube by transforming this property into a set of inequalities, into proving that a set of inequalities has no solution. So assume that I have a tube which is described by a nonlinear inequality which depends on the state and also on time t. So J corresponds to m inequalities. Okay. So I have some kind of cross-out solution, cross-out condition. So a cross-out condition has been illustrated on the picture here. Okay. It means that I have a trajectory that goes from inside to outside. So in this condition, if I have the cross-out condition, which tells me that this set of inequalities is not possible for all I, also I corresponds to an inequality, to one on the inequality, and if it is not possible to satisfy the cross-out condition, then J will be a capture tube. So let me explain maybe on the picture what means this. So I will come back and here I will have, let's say, the state. I will represent the state again as this one and this one. So this corresponds to x1 and here x2. And I will consider here, for instance, a part of the inequality. It corresponds to J1 of x and t up. I check the sign is negative. And I take another set, like this one, for instance. And this corresponds to J2 of x and t negative. If I take, let's say, the intersection here, then this corresponds to J of t. So J, it is a tube. So the intersection. If I have a trajectory, so if my state is inside, I want to prove that I will always stay inside. So what I want to find, is it possible from a trajectory at one time t, so I am on time t, to go out like this. So I represent like this. Is it possible for me to satisfy the cross-out condition? So for this, I will have first to find at time t. I will try to, so the yellow part corresponds to. So I will have to check first for this part. Okay, if it is not possible in this part, and then I will try to see if it is possible on this part. So I have two possible frontiers to go from inside to outside, either through J1 or through J2. So this part here corresponds, can be described by J1 of X and T smaller than 0, and J2 of X and T equals 0. Okay? And this part here corresponds to J, so it will be J1 of X and T equals 0, and J2 of X and T negative. So, or if you prefer, I can replace this by J, which contains J1 and J2 of X and T negative. So if I want to be more general, I just can write this not for J1 and J2, but I will write JA. So here, for instance, it will be A. And if I have this condition and this condition, so this part and this part, corresponds to the these two conditions. Now, I want also to go from inside to outside. So it means G dot should go from negative to positive. Oh, so now, when I want to go from negative to positive, it means that G dot is positive. Okay. So, excuse me. So the cross-out condition, I should add G dot of X and T should be positive. So since this is equal to the derivative with respect to x multiplied by f of x, I have an analytical expression for this. So I should first satisfy the go from inside to outside, but on this part of the frontier, then I will obtain what is written here. It corresponds to this theorem. And again, this can be proved using interval analysis easily, since proving a set of nonlinear inequalities has no solution can easily be performed with interval methods. So, with Vincent Doze, Stéphane Le Menec, and students from Bretagne, we made a software named BubiBex, like Bubble and Ibex, because it is a interval tool. We use a contractor programming tool, mainly made by Gilles Chabert, and to be able to prove that we have a capture tube. But of course, we need some inequalities for the candidate tube. Okay, so you have here a graphical illustration where, in fact, what we draw here yellow is some possibilities that a cross-out condition is satisfied. So in this case, what should we do when the cross-out condition it means that we have something like this. So the yellow part represented here. So you have some kind of track bar which represents the time. Here in the X, for the x-axis you have x1. Here you will have x2. And here you move with respect to time to see since the crossout condition should be satisfied for all t. So it means the yellow part here represents, in my picture before, this. So it represents the yellow part corresponds to small boxes like this. Okay. Up. Okay. So this is what represents. So if I have such a situation, such a box like this, what should be done? I have not a capture tube which satisfies the condition, but what I want here, it is I want to do more. I mean, I want to prove J is not a capture tube, but I want to compute the smallest capture tube which enclose J. So what can be done for this? I take this yellow part and I will integrate them using guaranteed integration. Okay, so I will integrate all the box. And if I have such a thing, so it's difficult to represent like this, maybe like this. So I integrate like this, okay. And so if here I have again a box, I will integrate like this. And at the end, I will obtain a tube. I will obtain a tube which encloses first the basic tube, the initial tubes, like this, okay. The initial tubes, but will also enclose all the integration part like this one. Okay, not so easy to represent, but if I consider all these tubes, which enclose the green initial tube with all part that has been added using the guaranteed integration, then I will obtain what we call the smallest capture tube, which enclose J of t. So J in this case is not a capture tube, but this will correspond to a capture tube. A simple test case to show how it works. I take a small robot which is described by a state equation where U1 and U2 are the inputs. I choose a control, and if I do this, my system becomes autonomous. But since U1 depends on T, I have a closed loop system which satisfies a time-dependent state equation. I choose a tube, like this one, where J1 and J2 say that I want my robot stay inside a bubble with radius R, and I want that the heading of the robot be almost the right one, so the right heading. And then I can check that for some parameters, say here, R equal to 4, then I am able to prove that I have a capture tube. For R smaller than 1, I can prove that some trajectory leaves J, so it is not a capture tube. So I have a tool, BBBEX is a tool which tells me possible if I have a candidate. Of course, if I have some parameters, it can help also, but to find the parameters. But if I have a candidate tube, then I am able to prove that this tube is a capture tube or not. But BBBEX is not at the moment able to compute a capture tube, just able to check that I have a capture tube. Okay? So now, what I want to do here is to to compute the capture tube. I will show first that the capture tube has a structure, mathematical structure, algebraic structure of a lattice. So lattice, what is a lattice? To have a lattice, I need an order relation. So here it will be the inclusion. And I will try to show what that means exactly in this context in a simple way. So I will maybe, okay, I will take here, good. I will, okay, draw some tubes. Here it will correspond to T, and here to X, the state, which belongs to Rn. What is a tube here? A tube, so I will try to draw one tube. This is a tube. It will be the red tube. And I will take a blue tube. So the blue tube will be like this. So the Tmax. So what happened here is that the intersection, so let's say this one is J1, is a tube which depends on T, and the blue one is J2. So I have a lattice because the intersection of the two tubes, so here, is also a tube. So in green, it corresponds to the tube J1 intersected by J2. Now, if I take this tube here, it will correspond in yellow to the union of the two tubes J1 and J2. Okay, so here it will correspond to Q1 union G2. So the set of tubes is a lattice because the intersection of two tubes is a tube and the union of two tubes is a tube. Now assume that the blue and red tube are not any kind of tube, but it is a capture tube. Both are capture tube. It means that the trajectory, once they enter in the red, they stay inside the red. Once they enter inside the blue, they stay inside the blue. In this case, we can understand that if the trajectory enter inside the intersection, then it will stay inside the intersection. Also, if it enter inside the union of two capture tubes, that it will stay inside the union. It means that if J1 is a capture tube, is capture. If J2 is capture, a capture tube, then it implies that the intersection is also a capture tube, but also the union is a capture tube. Okay. In this case, we can say that the set of capture tube is a sublattice of the set of tubes. So it is what is written here. The set of captured tubes is a sublattice of the set of tubes with respect to another relation which corresponds here to the inclusion. Okay. How can I compute captured tube? Since I have if I take a tube, any kind of tube, J, which is not a captured tube, as explained before, I can compute the intersection, or I can define the capture tube, the smallest capture tube, which encloses the tube J, as the intersection of all capture tubes which are greater than J. Okay, so since the set of capture tube is a lattice, the notion of smallest capture tube makes sense. Okay, we could not define the notion of smallest capture tube if the set of capture tube would not be a sublattice. Okay. So let me. Okay. So in this case, what will be my problem? My problem is that often I am able in practical situation to find a candidate to be a capture tube. But this candidate, most of the time, even if I have a good intuition for this candidate will not be a capture tube. So I will try to compute an interval, J1, J plus, which enclose a capture tube, because this capture tube will not be, I will not be able to compute this capture tube exactly. It cannot, this cannot be, so this cannot be represented inside the machine. So I can only have an approximation for this. So I will compute this one. Most of the time will correspond to this. And this one will be computed by the interval integration from, as explained, let me recall this, as explained, recall here. So if you want, the interval I want to compute will correspond, so I will call it J like this, of t. So it is an interval of t. Will have as a lower bound J of t. Okay, this one, and as an upper bound J plus of t, where J plus of t enclose this yellow part here, but also the green part here. Okay, so everything here belongs up, yes, everything here belongs to G plus. So it is explained here. I have a candidate J. I take all the trajectories that which all state, all pair xt which satisfy the crossout condition. I integrate them and I will obtain the capture tube. But this one cannot be computed exactly. I have some pessimism due to the interval integration. So in fact, what I am able to compute inside the machine is an inner approximation represented here and an outer approximation And this inner-outer approximation encloses the capture tube. More formally, to compute these capture tubes, I have to define the flow, so which corresponds to the solution from T0 to T1 of my state equation. Then to compute this capture tube, I will first take my candidate tube. I will add a set delta of J, which corresponds to all state pair, all pairs which correspond to X and T, which satisfy the crossout condition. And then I integrate with a guaranteed integration, and all the corresponding pairs will be added to delta J. And this corresponds to what I have to add to J to obtain the capture tube. Of course, I recall the crossout condition, which are defined by inequalities. So it corresponds to the part of the trajectory which goes from inside to outside the initial tube. And I have a representation here. I have my initial tube J, which is represented light gray. I take all points on the trajectory on the frontier of J, which satisfies the crossout condition. I integrate them, and I take all boxes. I will add all this part to J, and I will obtain the capture tube. Okay, and an outer approximation of the capture tube due to the pessimism of the interval integration. Okay, so here it's a small representation of an extension of BBBEX, which shows some part which do not satisfy the crossout condition. I integrate when I draw paint red. It means that I am outside the initial tube, but I go out. But if the control law is good, then I come back quickly to my tube J of T. Okay, let us consider a small test case. I have a test case, the same as taken before, which is described by state equation with dependent time. I have a candidate tube as this one, and this is not a capture tube. I mean, if I take the radius which depends on time and some trajectory, we can see that some trajectory leave J, so J is not a capture tube. So I have a representation here, some for one given time, so I have taken different times, T1, T2, T3, just to illustrate. The yellow part do not satisfy the crossout condition. They satisfy the crossout condition. I integrate them. So it is yellow, it is a new one that do not satisfy the crossout condition. So, excuse me. The yellow satisfies the new crossout condition for time T2, and the green one corresponds to the previous one. So that after integration. And again, so I have no new vectors, state vector which satisfy the crossout condition, only the previous one, which here, so the previous yellow boxes are integrated here to the green one. Of course, I do not represent the part of the state that enter inside J. After everything disappeared, it means that all yellow boxes have entered inside J. So I have some kind of discrete computing in a guaranteed way, the capture tube, which encloses the smallest capture tube, which encloses the initial tube. I have another example, test case 2, which is far much complicated, more realistic. Okay, the Dubin's car. The speed, you cannot control the speed, only the heading, so the speed is equal to 1. And I can control the rotational speed of the car, of the Dubin's car. I take the following controller, which tells me that I have a desired heading, and so to follow a trajectory, like this one. This is the target. I want to follow a given target. I have to compute the derivatives in order to obtain some analytical expression for the crossout condition. I have here the candidate tube, which is not a capture tube. It's this one. And we use some kind of extension of BBBX. And the tube is proved to be unsafe. So it is not a catch-up tube. But so it's the work mainly done by Vincent Doze and Stéphane Menec that were able to find J plus